So first of all, Happy New Year, everyone. Welcome to the first Joint Astronomy Colloquium of the new year. And it is a great honor and a privilege to have another new arrival to Heidelberg here today, Laura Kreidberg. Welcome. Laura is a world-leading expert on exoplanets, and specifically her work focuses on planetary atmospheres, their chemical composition and structure, and also eventually their potential habitability. Laura received her PhD in 2016 from the University of Chicago. She then moved to Harvard, where she was an I2C fellow, then a Clay fellow, and also was a junior fellow at the Society of Fellows. And since 2020, so since last year, she's the director of the new Apex department here at MPIA. And I have a rumor that we can share now, and that is that in an hour, it will be communicated that Laura receives the Annie Jump Cannon Award of the AAS this year in about an hour. So please don't tweet this yet, but I think it's a very festive day as well in that context. So yeah, thank you very much, Laura, for joining us. And to follow Joint Colloquium tradition, let's welcome Laura with a warm applause.
Always sounds meager.
It sounds very different than in real life, but it's the best we can do at the moment.
Thank you, everybody.
Yeah, so yeah, please, Laura, if you want to share your screen and...
Sure, yeah, Diedrich, thank you so much for the introduction. It's really a pleasure to be here, even virtually. And I will start with a disclaimer that some of this material, those of you who saw my COCO in December will have seen this already, but I never present exactly the same way twice, so there will be some new stuff. Good, so as you know, I'm the director of the new Apex department at MPIA. I want to say a few words of introduction. So the department was founded just last summer, it's brand new. We are focusing on exoplanet atmosphere characterization, both observational, theoretical, developing purpose-built instrumentation, which is really important for exoplanet atmospheres because the signal is so hard to measure, as well as studying their atmospheres in the lab. At the moment, we're involved in two major instrumentation projects, including METIS, which is a first light instrument for the ELT, as well as the upgrade to Gravity, Gravity Plus. And I do not have time to include those in my talk today, but if you're interested, please ask me afterwards and I'm happy to talk in some more detail. We're currently hiring. The job ads for this cycle have already passed, but this is not the last open positions that we will have. The ultimate size of the department will reach a steady state of more than 20 people. And at the moment, we are pretty small. So these are the current members of Apex. We have two PhD students, Sebastian Siba and Everett Nezedkin. Jason Dittman is an incoming postdoc who will be joining us hopefully in the next couple of months. And Ludmila Carone has also moved over from PSF to join Apex. So we're growing quickly, and it's a really exciting time to be here in Heidelberg. So I will briefly now give you a history of exoplanets. It's a new field, and so it's easy to do this quickly. 25 years ago, the first extrasolar planet was discovered, a hot Jupiter orbiting the Sun-like star 51 Pegasi b. And if you fast forward 25 years, we now know of over 4,000 confirmed planets around other stars, exoplanets, with many more coming quickly, both from ongoing surveys like TESS and KAPS, and those that will be on Sky in the next couple of years, like Plato. This plot shows the number of planets discovered every year, and I want to note that this is not a cumulative distribution. This is just the number of planets every year, so you can really see the acceleration in the rate of discovery. And if you boil all of this down to some statistical information, the most basic is that we know that planets actually outnumber stars in the galaxy, that sun-like stars typically host at least 0.7 planets, and that small stars, M-dwarf stars that are the most abundant, host on average 2.5 or more. And that these numbers are incomplete because we haven't yet been able to explore to the most distant planets from their host stars. And of course, the importance of this discovery was recognized with the Nobel Prize awarded to Didier Queloz and Michel Mayor. We have already seen that exoplanets are much more diverse than the planets of the solar system. This is a plot of planet mass versus distance from the host star, not corrected for any type of selection bias. And so you'll see a cluster of hot Jupiters in the upper left that are easy to detect. But what I want to draw your attention to is the diversity in these discoveries. So we've already uncovered an enormous population of very hot planets with orbital periods shorter than that of Mercury. The shortest orbital periods are less than a day for some of these planets. There's also a large population of planets that are intermediate in size between the Earth and Neptune. And I'll be focusing a lot on this population in my talk today. Backwards. There are also very massive planets on the boundary between planets and stars, and a whole bunch of really exotic different things. Planets with high orbital eccentricity or orbiting white dwarfs or even two stars. Some planets that are so hot that their surfaces are expected to be molten lava, etc., etc. And we haven't had a chance yet to explore a large part of this parameter space where most of the solar system planets lie. Now that we have found all of these planets, it's a really good time to characterize them in more detail. So that means measuring their masses, measuring their obliquities, and the focus of my research is to characterize their atmospheres. And what you can learn from the atmosphere is many, many things, including the formation and evolutionary history of the planet, which determines what the atmosphere is made of, how atmospheric physics is shaped by the extreme environments that some of these planets are found in, including planets that are very highly irradiated and tidally locked. And ultimately, we are perhaps most interested in whether there are other worlds out there that are suitable environments for life and whether some of those are even inhabited. So many people have recognized the promise of characterizing exoplanet atmospheres, and there's a whole bunch of techniques that have been developed to do this. In some ways, the most straightforward one is direct imaging, where you use a coronagraph to block out the central star and take an image of the planet directly, hence the name. Recently, gravity disrupted this picture, showing that it's possible to do K-band interferometry to measure spectra of the planet. Gravity actually spatially separates the planet from its host star, and you can put that light through a spectrograph and get a beautiful spectrum out of it. There's also a lot of ground-based observing you can do. There's high-resolution cross-correlation that use the fact that the planet is moving through its orbit, and if you can spectrally, if you have very high spectral resolution, you can actually detect the Doppler shift of the planet's lines as it moves through its orbit. And finally, there's traditional transmission and emission spectroscopy. The workhorse facilities for this type of observation have been Hubble and Spitzer. For a lot of reasons, it's easier to study planetary atmospheres from space than it is from the ground, simply because our own atmosphere is in the way. Although it's also possible to do this from the ground if you are clever in how you observe. And these techniques have been applied to planets with a very wide range of ages, orbital separations, sizes. And for my talk today, I'm going to focus very specifically on medium and small size planets and what we have learned about their atmospheres from Hubble and Spitzer, which have been some of the most impactful facilities in characterizing these planets in more detail. So I will give a very brief primer of how transmission and emission spectroscopy work. The basic idea is that this works the best for short period planets that are transiting. When the planet passes in front of the starlight will filter through the planet's atmosphere, where it can be absorbed and scattered. And so at wavelengths where the atmosphere is more opaque due to absorption from a molecule like water, for example, the planet appears a little bit bigger. And conversely, when the planet moves behind the star, any thermal emission or reflected light are blocked during the secondary eclipse. And so you can use these two techniques, transmission and emission spectroscopy, to infer the chemical composition, the cloud properties, and the climate of the planetary atmosphere. And to give you a feeling of what this looks like, this is a real color image of the Earth taken from space. You can see the beautiful blue Rayleigh scattering and the moon in the background. If you move into the infrared, that Rayleigh scattering signature goes away. So you can see that the Earth is a little bit smaller. And then if you move again farther into the infrared and target the ozone band, you can see that again, Earth looks a little bit bigger. And so if you toggle back and forth between these two wavelengths, you can see the distinct signature of ozone. And this is exactly the effect that we were searching for on exoplanets. So I love planets of all sizes, but I can't fit everything into one colloquium. So today I will focus on sub-Neptune sized planets, which I have divided into two populations. I'm calling them terrestrial planets and Neptini, which I will explain. So this figure shows the occurrence rate of planets as a function of planet size. This is a now famous plot from B.J. Fulton and collaborators. And you can see a couple of things jumping out right away. One of them is that small planets are more common than large planets. Planets below 4 Earth radii, roughly Neptune's radius, are about 10 times more common than larger planets. Not only that, but it appears that there are two distinct populations, one peaking at about 1 Earth radius and the other peaking at about 2.5 Earth radii. The first peak I'm calling terrestrial planets. Measurements of the masses for planets of this size show that they are consistent with Earth's bulk composition, so primarily rock and iron, whereas planets in the right-hand peak that I'm calling Neptini have to have a substantial volatile envelope, that is to say an atmosphere, to explain their observed masses and radii. However, it is not certain what that atmosphere is composed of. And for these smaller planets, roughly 2 to 4 Earth radius in size, there's a lot of degeneracy in models of their interior structure. And in order to break that degeneracy, you have to go and study the atmosphere directly to figure out what these things are actually made out of. So I'll start first with our efforts to characterize Neptini. And then I'll move on to terrestrial planets later. Okay, so as I said, Neptini are about 2 to 4 times the radius of Earth. They are expected to have at least some hydrogen in their atmospheres, but we don't know exactly how much. It could be anywhere between a less than 1% by mass to upwards of 50% by mass. There's some expectation that their atmospheres are enriched by planetesimal or pebble impacts. Or that for these smaller planets, there is because they don't accrete as much hydrogen, that their atmospheres are therefore metal rich. So it depends a lot exactly what model you choose for how these form, what the ultimate atmospheric composition is. So we can loosely expect some hydrogen, potentially a lot of metal enrichment, a lot of scatter. I'm showing predictions here from some modeling by Jonathan Fortney, predicting envelope metallicity as a function of planet mass. And in general, we'd expect higher metallicity for these smaller planets, but that's very model dependent. And so the goal of studying the atmospheres is to learn what process formed the planet. We hope to constrain things like the surface density of solids in the disk, how far away the planet was from the star, which will set the composition of the gas and solid material that's accreted, the relative efficiency of solid versus gas accretion. There's a lot of information there. However, the picture is more complicated than that. So it comes as no surprise that it's not as easy as what I just described. So I'd like now to show you where we are from an observer's point of view. And I'll start with my very first work on atmospheric characterization of these Neptini planets. And this is a transmission spectrum of GJ1214b. It is the most famous planet of this size. It's about 2.7 times the radius of Earth, with an equilibrium temperature of 550 Kelvin. And this is the most famous planet, or perhaps infamous, because it is the easiest to characterize. It is orbiting a nearby small bright star. And so purely from an observational standpoint, this is the single best sub-Neptune for atmospheric characterization. And so everyone went and observed it. And for a long time, for many years, all of the results were inconclusive. They showed that the transmission spectrum was featureless or consistent with a flat line. But the interpretation of that was not obvious, because there are two ways you can flatten the spectrum. One is to put high altitude condensates, so clouds or haze, in the atmosphere, which will truncate the spectral features at the cloud deck. Or you can increase the metallicity of the atmosphere, which will decrease the atmospheric scale height and also shrink the features. And so the work that I did on this planet the goal was to differentiate between the two scenarios, and we did that. At the time, these were the most intensive Hubble observations of any single exoplanet. We observed 15 transits in total with the Wide Field Camera 3 on Hubble in the near infrared. And our result is in the bottom panel here. And you can see that the spectrum is still flat. And so our conclusion was that clouds or haze must be present in the atmosphere. And not only must clouds or haze be present, but they have to be very exotic composition compared to the clouds that we're familiar with in the solar system. And so this is a toy model showing the posterior probability for a cloud top as a function of the composition of the atmosphere. Our toy model included hydrogen and water. And you can see that regardless of the atmospheric composition, regardless of how much water is present, the cloud top pressure has to be above about 1/10 of a millibar. And compared to Earth clouds, that's several orders of magnitude lower pressure. So these are really, really high up. There are a couple of possibilities for what clouds might form at these temperatures. Equilibrium chemistry predicts that salt and sulfide clouds will condense at 550 Kelvin. So this could be things like zinc sulfide or potassium chloride. Alternatively, you can produce hazes that are analogous to the Tholen haze on Titan. These are photochemical soots that are formed from methane molecules that are dissociated and then by high energy stellar flux, and then they're recombined to produce higher order hydrocarbons that may be easier to loft high up in the atmosphere. And in the years since then, the exoplanet atmosphere characterization community has worked very hard to build up the sample. We were discouraged at the beginning because a lot of the referees came back when we applied for telescope time and said, well, there's no point in looking at any more of these because the spectrum of GJ1214b is so flat, you won't learn anything. And that is absolutely not true. So over the past 6-7 years now, we've built up a sample. This is what it looked like in 2017. I'm showing on the left the transmission spectra of 6 of these sub-Neptune exoplanets sorted by their equilibrium temperature. And so you can see, if you look carefully, that the hotter planets tend to have larger spectral features. And I'm showing that again on the right. So this is the right-hand panel shows the H2O amplitude, the amplitude of the water feature at 1.4 microns as a function of planetary equilibrium temperature. And there's a very, very tentative trend that hotter planets tend to have clearer atmospheres. And you could explain this by perhaps having more materials that can condense as you move to lower temperature, or perhaps that below about 800 Kelvin, that's where you expect methane to become abundant, which is so good at producing these photochemical hazes. And so, of course, this is classic astronomy type of analysis. We had 6 objects, and so, of course, that's the right time to draw a line through them, but we really need a bigger sample size. So together with Ian Crossfield, we proposed a large Hubble program to add 5 additional planets to this sample. And we're starting to get some of the first results. Here's one of them. This is a transmission spectrum of the sub-Neptune HD 106315C. And I'm zooming into the Hubble data on the right. And if you squint at this, you can see that perhaps there's an increase in the transit depth at 1.4 microns. That would be characteristic of water absorption. And this is about a 2 sigma confidence result. We found the same thing for another planet in the sample. This is a 2.5 sigma detection of spectral features for HD 3167C, and this is work led by Tom Michael Evans. And in this case, none of these equilibrium models that I'm showing on the plot provide a very good fit to the data. We found that the spectrum is inconsistent with the flat line, but we weren't able to uniquely identify what absorber is present to produce, I think I don't have my pointer here, to produce that bump that you're seeing around 1.4 microns and then potentially an increase again at 1.6 microns. And so you can see these spectra, like I feel kind of like a proud parent of these spectra because we've worked so hard to get them. Just as an aside, I'll note that the error bars on the transit depth are smaller than 20 parts per million. And so we're able to measure the size of the planet to 2 parts in 10 to the minus 5 at each wavelength. And that is what is required to tease out the tiny features produced by atmospheres for these smaller planets. So moving ahead, this is what the demographics of Neptini look like today. So this is the same plot showing the amplitude of water absorption features in units of hydrogen helium scale heights. So we've accounted for the fact that these planets have different radii and different surface gravities. Shown as a function of equilibrium temperature, and the linear trend holds up really, really well, which was a big surprise to me and Ian Crossfield. We assumed that our sample size of 6 would not generalize very well to a sample size of a dozen. But it in large part appears to, except for K218b, which is a really interesting outlier at the coldest temperatures. And so our hypothesis is that perhaps as you move to the lowest temperatures below 350 Kelvin, the clouds may condense out of the observable part of the atmosphere, leaving you with a potentially clear upper atmosphere that you can study with transmission spectroscopy. And of course, there's only one object there, so I have another Hubble program in progress now to add another planet in that temperature range to this sample and see whether this holds up for additional systems. That would be really exciting because it would provide a way to see through the clouds in temperature regions that are really interesting. This K218b is in the habitable zone. And so while this particular planet is too big to be habitable, it would still provide a platform for us to study the chemistry of atmospheres in that temperature regime. Yeah, and we also are finding that for the temperature range of 500 to 800 Kelvin or so, that those planets tend to have the very smallest spectral features. And that may be because this could be a sweet spot for both cloud and haze formation, that you get equilibrium cloud condensation as well as photochemical hazes. And so if you want to look at planets that have the largest features, maybe the coldest ones or the hottest ones are the best places to look. So what can we do to see through the clouds? Our original question is, what are these atmospheres made of, and what does that teach us about their formation? And as you can see, we're still a long way from being able to do that, but there's a lot of progress that I expect in the next 5 to 10 years. So one of the things we really want to do is observe the spectra of the planets at longer wavelengths. And there are hints that the clouds become less opaque beyond 2 microns or so. This is a result from Bjorn Bennecke for GJ3470b, showing that you get the by now familiar very small water feature between 1 and 2 microns. And then as you move farther into the infrared, you can see from Spitzer data from one of my programs that the transit depth goes down and the amplitude of features goes up. And so this is consistent with the picture of the atmosphere where the cloud particles are small, about 0.5 micron in size. Another direction we could take is to observe hotter planets. And these are new Spitzer observations of a hot Neptune discovered by TESS. This is LTT 9779b, a roughly Neptune-sized planet that has an equilibrium temperature in excess of 2000 Kelvin. So it's really hot. And previously, these planets had not been found prior to TESS, in part because they're really rare. The issue is that if you take a small planet and you bring it very close to its host star, the atmosphere can easily photoevaporate, leaving you with an evaporated core. And so the hottest Neptunes, like this planet, are relatively rare. We observed this planet with Spitzer. The emission spectrum, or the 2 Spitzer photometric bands, are shown on the left. Tentatively, this looks like CO or CO2 absorption at 4.5 microns. We also observed a thermal phase curve, which we binned into 3 data points. That's shown on the right, and this was work led by Ian Crossfield, where we found, excitingly, that none of the 3D models provided a good fit to the data. That's always a fun place to be in scientifically when the model predictions don't work out. The amplitude of the phase curve is larger than expected for a solar composition atmosphere. If you add a lot of metal to the atmosphere, it means that you can't see as deep down. And that is, in that case, you don't expect, I need a chalkboard to explain this. If you're not seeing as deep in the atmosphere, you expect a larger temperature contrast between the day side and the night side, because there's not enough time for heat to recirculate at those very upper altitudes. So the amplitude of the phase curve is consistent with a higher metallicity composition, but on the other hand, the absolute level does not provide a very good match. So I'm comparing the blue and the red curves in the right-hand panel. And so this sums up to, I would say, tentative evidence that this planet has a higher metallicity atmosphere, but it's really hard to tell for sure with the quality of the data that we have. And finally, of course, the thing that we want the absolute most is observations with JWST. So this gets us not only longer wavelength coverage, but also higher precision spectra. This is a mock retrieval for a sub-Neptune from Everett and Zedkin. Typical Hubble data are shown in the inset in the left-hand panel, and you can see that there are different models that can produce the same type of spectrum that show very distinct differences as you move into the infrared. And so we show here 2 limiting cases, one with a high metallicity composition, about 100 times solar, that has strong absorption from CO2 between 4 and 5 microns. And we show another limiting case of a lower metallicity composition, solar composition, with high altitude clouds. And a transmission spectrum from JWST will be able to really cleanly distinguish finally between these possibilities. And so this is something that the exoplanet community is really excited about. Okay, so to sum up what we have learned about Neptini, if you take away any one point, it should be that not all of the spectra are flat, so we should continue to observe these. There's a lot that we can keep learning about them as we keep trying, not only because we have new observing capabilities coming online, but also because TESS and other surveys are rapidly finding all of the best targets in the sky. The planets where we're most likely to see spectral features are probably the hottest ones, although also potentially the coldest ones. And that these trends may be explained by condensate formation, cloud and haze formation in the atmospheres. There's a couple of plausible strategies to see through the clouds. We can observe at longer wavelengths, we can observe hotter or potentially colder planets. And after all of this work, we still do not know observationally what the atmospheres are made out of, but that we should expect a lot of progress in the next 5 years, particularly once we start measuring spectra with JWST. Okay, so for the second part of my talk, I want to switch gears now and focus on terrestrial planets, which have a lot of the same questions as we have for Neptini. We want to know what their atmospheres are made out of and what their climates are like. But stepping back, we are not sure a priori whether an atmosphere is present or not. We cannot measure the mass and the radius precisely enough to tell whether a volatile envelope is there. Typically, a high mean molecular weight atmosphere like Earth or Venus will contribute about 1% to the radius of the planet. And we, don't have the precision to measure that. We don't understand the stellar properties well enough to detect that difference. And there's also a lot of degeneracy with the amount of iron in the core. And so the only way for an Earth-sized planet to determine whether it has an atmosphere is to study it directly. We expect diversity. So I'm showing here a cartoon of the planets in the solar system where we have 2 that have maintained thick atmospheres, that's Venus and Earth, and 2 that have not, that's Mercury and Mars. And the reasons for this are varied. So we think that the factors that shape the secondary atmosphere of a terrestrial planet range from what volatiles were delivered early in its formation to disruption of the atmosphere by giant impacts later on, to outgassing via volcanism, drawdown of materials via plate tectonics as the planet evolves over time. And of course, on Earth, we know that the atmosphere has been really dramatically shaped by the presence of life. And so all of that points to a wide range of atmospheric compositions and masses for other Earth-sized exoplanets. And not only that, but the 4 examples we have in the solar system all share a common host star, which is our own sun. And we know that planets around M dwarfs are more numerous. And so it is, in my opinion, it is one of the most fundamental questions for exoplanet science, whether or not the rocky planets around M dwarfs tend to have atmospheres and under what conditions, because they're simply the most numerous in the galaxy. And this provides kind of a blessing and a curse at the same time. So not only are planets around M dwarfs abundant, they are also easy to characterize thanks to their small host stars. It's very, very simple. The smaller the star is relative to the planet, the larger the signal from the planet's atmosphere. On the other hand, the atmospheres of these planets are in danger in a way that atmospheres of Earth-like planets around sun-like stars are not. And there's a couple reasons for this. So one of them is photoevaporation. And this is more pronounced for M dwarf hosted planets because these small M dwarfs spend a long time contracting to the main sequence. In their early lifetimes, they're very bright in the ultraviolet, and that can contribute to many Earth's oceans of water being photoevaporated when the planet is young. A lot of the planets with equilibrium temperatures that are interesting to us, so including the habitable zone, are expected to be tidally locked. M dwarfs are so much cooler than sun-like stars that the habitable zone, a habitable planet may have an orbital period of weeks rather than a year. And at that close orbital distance, the tidal force of the star will lock the planet, and that can also be problematic for your atmosphere. This is because if you have a hot night side, if you have a hot day side and a cold night side, you may have all of your volatiles, all of your water, for example, freeze out on the night side, leaving you with one icy half that never sees light from the star, and bare rock on the other side. So this sounds really scary, but there are ways around all of these problems. If you can outgas material from volcanic activity later in the planet's life, and so even if the atmosphere was lost during the pre-main sequence phase of the star, you can revive it from outgassing. And in addition to that, you can, if you put an ocean on your planet, that helps with heat circulation between the day side and the night side, and et cetera, et cetera. So the punchline is that we just really don't know, and we have to look. There's been a lot of observational effort devoted to characterizing the atmospheres of these planets, starting mainly with transmission spectroscopy. A lot of this has been focused on the famous TRAPPIST-1 system of 7 terrestrial planets around a nearby ultra-cool dwarf star. There have also been observations of GJ 1132b and several others now from both Hubble and telescopes on the ground. And the upshot of all of this work is that the spectra tend to be featureless, thereby ruling out cloud-free, hydrogen-rich atmospheres. And this, I would argue, is a good thing because we don't expect small planets to have hydrogen-rich atmospheres anyway. And this is because you can't, if the atmosphere were hydrogen-rich, it would have to be exceptionally finely tuned. So not only can you not have very much atmosphere, otherwise it would increase the radius of the planet to larger than is measured, but it would have to be stable on gigayear timescales. And hydrogen is the lightest molecule you would expect in an atmosphere, and it's the easiest to photoevaporate. And so all of this is hanging together. We don't expect hydrogen-rich atmospheres anyway, and the data show that they are not there. But we still don't know if we still don't know whether the atmosphere simply has a high mean molecular weight instead, whether clouds are present similarly to what we found for GJ 1214b, or finally, whether no atmosphere is present at all. There's a different approach you can take to determining yes or no whether an atmosphere is there. And this is a technique called thermal phase curve observations that I have a cartoon to illustrate. So the idea is that for a tidally locked planet, it's orbiting around its host star. As it moves through its orbit, you are exposed to different faces of the planet. Here, the hot day side is rotating into view. Now the planet is being eclipsed by its host star. And here the day side is rotating back out of view. And unfortunately, we're not able to measure, we can't actually see the top of this cartoon, so we can't spatially resolve the planet and the star, but we can measure the brightness over time. And this gives us a climate map. Temperature is a function of longitude for the planet. And the idea is that the thicker your atmosphere is, the better it is at redistributing heat. So a very large temperature contrast between the day side and the night side means that minimal or no atmosphere is present. Whereas if you have a thick atmosphere, it tends to homogenize the temperature difference between the day side and the night side. And this idea was suggested by a lot of different groups, but it wasn't possible to put into practice until recently. And one of the very first planets discovered by the TESS mission is LHS 3844b. This is the first terrestrial exoplanet that is accessible for this type of observation. The previous smallest one was 55 Cancri e, so aficionados in the audience will recognize that name. But that planet is about 2 times the radius of Earth and is too large to be truly, truly rocky with a solid surface. So along came LHS 3844b. This is exciting because it's part of the abundant population of rocky planets around M dwarfs. It's 1.3 times the radius of Earth. It's orbiting a nearby small star. What makes it special is that its orbital period is really short, only 11 hours, leading to an equilibrium temperature of about 1,000 Kelvin. And this is perfect because it is hot enough for thermal emission to be detected with current facilities, but not so hot that the atmosphere would necessarily be lost. And for example, a CO2 atmosphere could remain stable at this temperature for many, many years, many, many gigayears. So I got really excited and I decided to go big or go home and write a Spitzer proposal for 100 hours of observing time. Fortunately, this discovery was made in the last, I think, 6 months of Spitzer's lifetime, so the timing was really lucky. The idea was to observe 9 continuous orbits of the planet at 4.5 microns. And luckily for me, the proposal was accepted. And this is what we measured. This is the phase curve of LHS 3844b. So it's beautiful. You can see the secondary eclipse there at orbital phase 0.5. That's more than a 10 sigma detection. You also will note that the temperature contrast between the day side and the night side is very large. That leads to the large measured amplitude that we found. The day side temperature is consistent with is over 1,000 Kelvin, and the night side is consistent with 0. And there's no detectable hotspot offset, which is another signature of atmospheric circulation that can transport heat from the day side to the night side. So all of this points towards most likely no atmosphere on the planet. But we wanted to make very, very sure. So I assembled what I call my dream team of theorists to model what types of atmospheres might possibly be consistent with what we measured. This plot shows the predicted eclipse depth as a function of surface pressure of the atmosphere. You can see the blue models are different compositions, and these show that the higher the surface pressure is, the smaller the eclipse that is predicted, and that's because these thick atmospheres will move heat around to the night side. The measured eclipse depth for this planet is shown in gray at the top of the plot. And we considered mainly oxygen and carbon dioxide mixtures for the atmospheric composition. This is expected for rocky planets of this temperature. And we found that no matter what we assumed for what the atmosphere is made out of, the data rule out surface pressures greater than 10 bars at over 3 sigma confidence. We also looked at whether thinner atmospheres would be stable over the planet's lifetime. And this is work led by Laura Schaefer at Stanford. This plot shows the final pressure of oxygen in bars as a function of the initial water abundance of the planet, so how much water it formed with, and the UV brightness of the star during its early lifetime. And you can see that the lower right of this plot is a region where we would expect the atmosphere to be completely lost. You're left with a partial pressure of oxygen less than 10 to the minus 10 bars. The upper left of the plot is excluded by our data. So this is a planet that would form with a lot of water and it would have a lower UV brightness of the star. There is a small region of allowed pressures that give you a planet with substantial atmosphere that we couldn't detect. But that's very finely tuned. So not only would you have to have a very, very specific initial abundance of water on your planet, but you would also have to have a lower than expected UV brightness for the star. A typical M dwarf is marked with the red dot on the x-axis. And so we think that's not very likely. It's too finely tuned. So our conclusion is that most likely what we are seeing is thermal emission from the rocky surface of a terrestrial exoplanet for the first time. And our next question, of course, is what kind of rock are we looking at? And these are models from Renyu Hu showing the predicted thermal emission spectra for different types of rock. Our Spitzer data is shown with a black cross at 4.5 microns. And based on this modeling, we found that the best fit compositions are basaltic in nature. They have to be fairly dark, low albedo rocks to produce as hot of a dacite as what we're seeing. Basaltic rock could be produced from volcanic activity. It's analogous to the lunar mare and the surface of Mercury. If you've ever had the pleasure of going to Hawaii to see the black sand beaches there, that's basalt. And so possibly what we're seeing is evidence for a history of rampant volcanism on the surface of this planet. Again, we have a lot to look forward to with JWST. This is a simulated data set for 3 Miri eclipses of the same planet, LHS 3844b, compared to different rocky surfaces. And you can see that not only do you will we get a really tight measurement of the albedo of the planet, but we can also start to distinguish between different rocky surface types. So with a measurement like this, we could measure the surface fraction of basalt to a precision of about 10%. So we could detect the dominant rocky constituent, and we could, if the surface is made out of 2 types of rock, which is plausible based on what we've seen in the solar system, we might be able to start to distinguish whether it's pure composition of only 1 rock or a mixture of 2 different types based on the shape of these spectral features. Not only that, but JWST will also open the door to making this measurement for a much broader sample of planets. Tens of rocky planets will be accessible, and we'll be able to answer the question I originally posed, which is how often do rocky planets around M dwarfs tend to keep their atmospheres? For the best cases, if an atmosphere is present, we'll be able to detect spectral features from the dominant chemical species. I'm showing a simulation from work led by Caroline Morley for the emission spectrum of TRAPPIST-1b for different assumed compositions. The blue model is a composition dominated by water. The orange model is dominated by methane, and the red model is dominated by CO2. And so people talk a lot about biosignatures, but for now, in the next 5 years, the measurement I'm most excited about is this very basic chemical inventory of what's in the atmosphere. Like, does it have water? Does it have CO2? Does it have an atmosphere at all? We're in the wild west of characterizing rocky planets. And so the 0th order questions are the ones where we're going to see the most progress in the next decade. And all of that will lay a really important groundwork for designing future missions. So I'm sure all of you are familiar with these big flagship mission concepts that are under discussion by the Decadal Review, among others, trying to decide what our next big space telescope will be. And I personally am very supportive of a direct imaging mission in the future that will be so big and so great that we'll be able to not only get this basic chemical inventory type of information, but really start to search for signatures of life. This plot is a classic showing the reflectance spectrum of Earth. There is such rich information in this. You can see spectral features from a lot of different chemical species, most notably the simultaneous presence of oxygen and methane, which are out of chemical equilibrium. Normally they would react with each other, form CO2 and water. Instead, we see them here together on Earth, which is classically considered the smoking gun evidence for life. And so my hope is that the work that is done with JWST, studying the atmospheres of the best planets discovered by TESS, everything that's coming together in the next 5 years or so, we will have a good starting point for the design for knowing what to expect for Earth-like planets that will help us prepare for one of these big direct imaging missions. All right, so I have just a couple minutes left. I think I've talked enough for now. I'm happy to take some questions. Stop my share.
Very much, Laura. That was really, really fascinating. I'm sure there are going to be many questions. While I wait for hands to go up using the Zoom feature, I'd like to ask a first question myself, because it's clear that this is really the technological forefront. It's pioneering basically new ways of trying to characterize these atmospheres. A question that's always on my mind is, what is necessary to turn this into statistics in the long run, right? Because you mentioned with James Webb, you're going to tens, that's maybe the start of statistics, but like the Kepler revolution, how would you build a Kepler revolution for atmospheres? And that's
thank you. That's a great question, and something I didn't have time to get to at all is another planned mission called Ariel, which is designed to do exactly this. It will be a statistical survey of a sample of 500 to 1,000 planets. It is smaller than JWST, and so really pushing to these Earth-sized planets will not be possible for Ariel. But certainly for the sub-Neptunes, we'll be able to build up a statistical sample. And for the Earth-sized planets, this is one of the questions that comes up all the time is how big of a sample do we need to say something interesting? And the number that gets thrown around a lot is 100. Unfortunately, that would be many billions of dollars to build a telescope that could directly image 100 planets. But if you push it down to 50, we're walking the line between what is interesting and what is possible. And so I think it's fair to state as a goal getting spectra of 50 Earth analogs. And that would be enough to start making a statistical assessment.
Yeah. Okay. Thank you. Ben, go ahead.
Yeah. Awesome talk. Really unbelievable stuff. I'm curious about the measurements you can make on planets that you've ruled atmospheres out for, looking at their geologic composition. Is there any way in which you can use that to sort of characterize, or perhaps from the other end, is there uncertainty related to the actual geological sort of layout of the planet? Like a recently resurfaced smooth planet, I assume, would have a slightly different reflectance and spectra than something quite mountainous or dust or boulder covered.
Yeah, that is an excellent question. And if the picture that I presented is definitely an astronomer's view of geology, and it's more complicated than that. There's all kinds of factors, everything from the typical, like, are you seeing fine sand? Are you seeing large boulders? How has the rock been weathered from cosmic rays over time? Things like that. And the short answer is that some features are really robust. So there's something called the Christensen feature that's really strongly associated with silicates that, to my knowledge, there's no other way to get it. Other features, subtler things like slopes, I think we need better lab data to be able to tell. And because this is fairly new and this is a temperature range that hasn't been explored in the solar system very much, the lab data is lacking. So that's another thing that I'd like to see in the next 5-10 years, is more real measurements of hot rocks in the lab to see what their spectra look like.
So another question that I had is how important, well, it's pretty clear from your talk that the infrared part of the spectrum is really critical. But of course, there are going to be surveys like LSST that do a lot of very sensitive photometry over a large part of the sky. How useful can that be eventually in trying to characterize atmospheres, or is that just basically impossible because of the thickness variations being too small?
LSST is really tough just because the cadence is so long. There is work that you can do in the optical with TESS, KOPS, and Plato, for example, to look at reflected light. It would be awesome to look at the phase function in the optical for some of these hot rocky planets, because that would tell you something about the previous question, like, are you looking at sand? Are you looking at boulders? The precision, and that's really pushing the precision of what we'll have access to. It depends. This is one of those things, if nature is kind and we get the perfect target, then maybe we can detect it. And yeah.
Okay, that's clear. Thank you. So I'll, as we're coming up to the hour, I'll give a final chance to ask questions. Ben, you still have your hand up, but I suppose that's from last time. Gregor, please go ahead.
Yeah, hello. So apparently there was a publication just today about measuring polarized light from exoplanets from the Netherlands. I wonder if there's any chance of measuring some atmospheric properties using polarization in the future, given future instruments.
Yeah, so the polarization signal is very sensitive to the cloud properties. But because it's so observationally challenging, I think in the near future we shouldn't expect this for any planet smaller than Jupiter.
Yeah.
Yeah.
Okay, thank you.
Okay, now then, before we thank Laura again, I would like to briefly announce next week's colloquium, and I'll share my screen for that. So next week we'll have a colloquium by Connie Aerts, who's here affiliated with MPIA, of course, as well, as her home institution in Leuven. And she's going to talk to us about space astroseismology and the renaissance of stellar interiors. So I look forward to seeing everyone again next week for Connie's talk. And please let me ask you all to unmute to, again, give Laura a very warm thank you, and also to take the opportunity, because we have 5 seconds remaining, to congratulate her with the Annie Jump Cannon Award. So thank you again, Laura, and congratulations.